Welcome to the last week of our course Analysis of a Complex Kind. We'll study infinite series, power series, Taylor series this week, and we'll even get to the Riemann zeta function as well as the Riemann hypothesis and its relation to prime numbers. Let's start with the definition. An infinite series is just an infinite sum. We're going to add up infinitely many numbers. What does that mean? We say such a series converges to a number s, and this s is also going to be a complex number, if the sequence of partial sums, so the sequence you get when you stop at a certain point, and then you move that point farther and further back. So if the sequence of partial sums given by the first n members of the sequence converges to s. These AKs are complex numbers. You've probably seen infinite series before in the context of real numbers. Now these AKs are complex numbers, and one can easily see that a series of complex numbers converges if and only if the corresponding series of real parts converges and the corresponding series of imaginary parts converges. Let's start with an example. Consider the series of z to the k's for some z and c. So for example, if z was equal to I over 2, then the series would be for k is equal to 0, you get 1. For k equals 1, you get I over 2. For k equals 2, you get I squared over 4. Then you get I cubed over 8, and so forth. You could split that up into real and imaginary parts, so you have 1 minus 1/4, and the next one is going to be this one, is going to be plus 1/16, and so forth. And then the corresponding imaginary parts are this one right here, I over 2, so 1/2, and this one here, I cubed is minus I, so minus 1/8, and then plus 1/32, and so forth. So you could look at the sequence that way and determine for each particular z whether the two corresponding real series converge, or we can look at this series more generally for a general z and try to figure out if we can find a general way to figure out where the series converges, and that's what we're going to do. The partial sums are given by simply adding from k equals 0 to n, so 1 plus z squared plus z cubed, all the way to z to the n. And here's a great trick to find a closed formula in order to help us figure out whether these partial sums have a limit as n goes to infinity. So here's the trick. Sn again is the sum from 1 plus z squared all the way to z to the n, and now we look at z times Sn. So in other words, we need to multiply each term by z. Well, 1 times z is z times z squared, and so forth, all the way to the last term, z to the n times z is z to the n plus 1. So z times Sn is pretty close to Sn, except for that missing first term, that 1 isn't here, and the extra last term. So when I take Sn and subtract from it z times Sn, most of the terms cancel out. All that's left is this 1 from the Sn term, and the extra zn plus 1 from the z times Sn term. So Sn minus z times Sn is 1 minus z to the n plus 1. But now here on the left-hand side, I can factor out an Sn. That's Sn times 1 minus z. And so I can divide both sides of the equation by 1 minus z and find that Sn is 1 minus z to the n plus 1 over 1 minus z. And all of a sudden, I have a closed form expression for Sn, and I can figure out whether it converges as n goes to infinity. And it turns out that depends on what the value of z is. Remember, if z is less than 1 in absolute value, and if I take higher and higher powers of z, then the higher and higher powers of z converge to the origin. On the other hand, when z is bigger than 1 in absolute value, then the modulus of the powers gets larger and larger and larger, and z to the n goes to infinity. When z is equal to 1 in absolute value, then the powers of z simply walk around the unit circle, but they don't converge because they keep walking around the unit circle. In other words, if z is less than 1 in absolute value, then this term z to the n plus 1 goes to 0, so that in the limit, Sn goes to 1 over 1 minus z, and we can say that the sum from k equals 0 to infinity, so that series we're looking at, equals 1 over 1 minus z, for z less than 1 in absolute value. So what happens when z is greater than or equal to 1? Here's a theorem. If a series converges, then these AKs must go to 0 as k goes to infinity. So it's a necessary condition for the AKs to go to 0 for the series to converge, but it's actually not sufficient. There are examples of series where the AK terms do go to 0, yet the series does not converge. They don't go to 0 fast enough to make the series converge. So these AKs have to go to 0 at a certain rate. So, but if the series converges, then the AKs definitely have to go to 0. In our example, if z is greater than or equal to 1 in absolute value, then certainly z to the k does not go to 0. It actually goes to infinity if z is bigger than 1 in absolute value, and it stays at 1 in absolute value if z is of absolute value 1. And therefore, the series of the z to the k's cannot converge by this theorem because these z to the k's don't go to 0. We say the series diverges for z greater than or equal to 1. Let's now analyze the real and imaginary parts of this equation. So we found that for z less than 1, we have the sum of the z to the k's is 1 over 1 minus z. What does it tell us about the real and imaginary parts? Let's write z in polar form as r e to the I theta. Then z to the k can be found by taking the radius to the power k, and by de Moivre's formula, e to the I theta to the kth power is equal to e to the I k theta. And e to the I k theta, that is cosine of k theta plus I sine of k theta. So therefore, the sum of the z to the k's is the same as the sum of r to the k cosine of k theta, that's the real part of the series of the z to the k's, plus I times the sum of r to the k sine of k theta. So that's the imaginary part. So we just rewrote the left-hand side of this equation in terms of real and imaginary part. Now, let's rewrite the right-hand side of the same equation. So what is 1 over 1 minus z? How do we split that up into real and imaginary part? Again, we write z as r e to the I theta, and we remember a trick. In order to find out 1 over a complex number, we multiply top and bottom by the complex conjugate. What is the complex conjugate of r e to the I theta? The complex conjugate of this number is 1, because 1 is real, minus r is real, and so we need the conjugate of e to the I theta, which was e to the minus I theta. So we multiply top and bottom by that. The top we can expand because e to the minus I theta, recall, is cosine of minus theta, but cosine of minus theta is the same as cosine of theta because cosine is an even function, plus I times sine of minus theta. But sine of minus theta is minus sine of theta, because sine is an odd function. So the top becomes minus r times cosine theta, minus minus, so plus r times sine theta times I. The denominator we can multiply through. We have 1 times 1 equals 1, 1 times r e to the I theta, you see right here, and there's a 1 times r e to the minus I theta, again with a negative sign in front of it, and then r e to the I theta times r e to the minus I theta, which gives you this r squared. In the denominator, we have a term minus r times e to the I theta plus e to the minus I theta. But e to the I theta plus e to the minus I theta, if we were to divide that by 2, that will be cosine theta. We can't just divide by 2. We have to then multiply by 2 to make it right. So the denominator, these two terms here in the denominator, equal minus r times 2 cosine theta. And that's what you see here on the right. Altogether, we have found the real part of 1 over 1 minus z right here, because these are all real, and the imaginary part is right here. We also found the real part of the sum of the z to the k's, that's right here, and we also found the imaginary part, that's right here. Because we have an equality right here, left-hand side and right-hand side are the same, that means that the real parts must agree with each other, and the imaginary parts must agree with each other. In other words, the real parts agree, so r to the k cosine k theta, the sum of that, must equal 1 minus r cosine theta divided by 1 minus 2 r cosine theta plus r squared, and that's what you see right here. Furthermore, the imaginary parts must agree, so the sum of r to the k sine of k theta must equal r sine theta over the same denominator that we had before. Here's another example. Let's look at the sum of I to the k over k, for k from 1 to infinity. Does that series converge? Let's write out a few terms. Notice that the series starts at 1, because we can't really have it start at 0, we will be dividing by 0. We don't want to do that. Series can start at other points, and it doesn't really influence their convergence, because we're talking about finitely many terms which have something to do with the value of the series, but not whether or not they converge. So for k equals 1, we get I over 1. For k equals 2, we get I squared over 2, so minus 1/2. For k equals 3, we get I cubed, which is minus I over 3. For k equals 4, we get I to the 4th, which is 1 over 4. And then we keep going, plus I over 5, minus 1/6, minus I over 7, plus 1/8, and so forth. So does the series converge? Again, we can split it up into real and imaginary parts, or let's first of all start by looking at the series of absolute values. The absolute value of I to the k over k is simply 1 over k. This series right here is known to be the harmonic series, and it is known to diverge. Even though 1 over k definitely goes to 0, as k goes to infinity, it's not sufficient for convergence of the series. Here, by the way, is a way to see why the harmonic series does not converge. You could write the series of the 1 over k's as 1 plus 1/2 plus 1/3 plus 1/4, and then we group these numbers in a certain smart way. We group 1/3 plus 1/4 together, and observe, well, 1/3 is greater than or equal to 1/4. And so this term, 1/3 plus 1/4, is greater than or equal to 1/4 plus 1/4, which is 1/2. Similarly, we group 1/5 through 1/8 together, and observe 1/5 is greater than or equal to 1/8, 1/6 is greater than or equal to 1/8, 1/7 is greater than or equal to 1/8, and 1/8 is equal to 1/8. So altogether, these four terms are greater than or equal to 4 times 1/8, which is 1/2. And then we take the next 8 terms and do the same thing, and we keep being able to squeeze out 1/2s, lots of 1/2s. We get infinitely many 1/2s, which means the series becomes as large as we want to. It does not converge. If I stop anywhere, the partial sums keep getting bigger and bigger and bigger by significant amounts, and therefore the series diverges. So if I put absolute values around the terms of the series, it diverges. But how would the series itself, without the absolute values? Does it converge? So we'll have to split it up into real and imaginary parts like I did at the top. And we noticed when we wrote out the individual terms of the series, when k is even, then we take I to an even power and make it a real number. It's either 1 or -1 that we get. So when k is of the form 2 times n, where n is a natural number, then I to the k is really I to the 2n, and I to the 2n could be written as I squared to the power n, so which is -1 to the n. That's definitely real, it's 1 or -1. On the other hand, when k is odd, then k is of the form 2n plus 1, those are all odd numbers, then I to the k is of the form I to the 2n plus 1, and I could write that as I times I to the 2n, and since I to the 2n is -1 to the n, this I to the 2n plus 1 becomes I times -1 to the n. That's purely imaginary. It's either I or -I, depending on whether n is even or odd. Therefore, the series of the I to the k's over k's can be split up into the real part, which is this one right here, and the imaginary part, which is this one right here. Notice that the first series we start with n equals 1, because the first even number we get that way is 2, which is the smallest even number we have. The second series I'm starting at n equals 0, because when n is equal to 0, I get the exponent 1, the first odd number. So it starts at the correct first odd number. We can now simplify a little bit. I'm going to pull this 2 in the first series outside of the series to get this 1/2. I rewrite I to the 2n as -1 to the n, and so the series becomes 1/2 times the sum of -1 to the n over n. It looks almost like the harmonic series, except for the -1 to the n right there. And the second one, I'm going to pull one I out of there, therefore finding a -1 to the n in the numerator and 2n plus 1 in the denominator. Now let's look at these two series. What is the sum of -1 to the n over n? That's called the alternating harmonic series, because it's almost like a harmonic series, but the signs alternate between 1 and -1. And the claim is the alternating harmonic series converges. How would you see that? Well, you can see that by actually drawing a number line. Say 0 is here, and -1 is here. And let's look at the values of the series. We start at -1. That's the first partial sum. Then we add 1/2 to that, so we get to here. -1 plus 1/2. Next, we subtract 1/3 from that. So maybe that gets us here. -1 plus 1/2 minus 1/3. Next, we add 1/4, which is less than I subtracted before. Next, I subtract 1/5. Then I add 1/6. I subtract 1/7. I add 1/8. And you can see that this will narrow down onto one point somewhere here. The sequence of partial sums actually converges. One can make this precise. But that's the main reason why the alternating harmonic series converges. A similar argument leads to the imaginary part here converging as well. So therefore, the series of the I to the k over k's converges. It just didn't converge when you put absolute values around it. So there's a difference there. We call it absolute convergence. We say a series of complex numbers converges absolutely if you can just put absolute values around the ak's in the series, then converges. We've seen examples. The series of the z to the k's actually converges or converges absolutely as long as the absolute value of z is less than 1. The argument that we gave for convergence doesn't change. You can still find the partial sums and nothing changes. So the series converges and also converges absolutely as long as the absolute value of z is less than 1. On the other hand, the series of the I to the k over k's converges, but not absolutely. Here's the theorem. If a series converges absolutely, then it also converges. The reverse is not true, as we just saw. We saw an example of a series that converges, but it does not converge absolutely. So absolute convergence implies convergence, but the reverse direction is not true. Furthermore, you have an infinite version of a triangle inequality in that case. The absolute value of the original series is bounded above by the sum of the absolute values of the A case. Let's look at an example. Let's again look at the series of the z to the case. We know it converges absolutely as long as the absolute value of z is less than 1. Therefore, the previous theorem tells us the absolute value of the sum is bounded above by the sum of the absolute values. And since the absolute value of z to the k is equal to the absolute value of z to the k, that's what I wrote over here. But the left-hand side, we found to be 1 over 1 minus z. This is the value of the sum, and then we simply put absolute values around it. The right-hand side equals 1 over 1 minus the absolute value of z, because I'm adding powers of the absolute value of z here. So the same argument we made earlier to find the value of the series can be applied to find that the value of this series is 1 over 1 minus the absolute value of z. Therefore, this inequality right here shows that the absolute value of 1 over 1 minus z must be less than or equal to 1 over 1 minus the absolute value of z. By the way, you could have found the same inequality simply by observing that 1 minus z, the denominator of this expression, is greater than or equal to, by the reverse triangle inequality, 1 minus the absolute value of z. And then taking reciprocals, which will flip the sign around, you get this inequality. In the next lecture, we'll study specific series, namely power series. These are series that are of the form sum k from 0 to infinity, a coefficient, times z minus z0 to the k. We'll study these for a fixed value of z0, and we'll let z vary. And as z varies, it turns out these series form analytic functions as long as we are within the region where these series converge.